Hello, Math Ninja here. Today we are here to talk about the Permutation Group, new group today. Also, two more things, subgroups and also isomorphisms. All very important topics. Permutation group is one of the good examples of a non-abelian group. It uses composition, it is nice. I like bijections. The subgroups, it is another example in mathematics where you have a subset of a subset of a certain object having the same properties as the bigger object. Subgroup, for example, subclass. There's lots of sub stuff. A subset. Many of them. Anyways, that's the second thing. The third thing we'll be talking about, very important concept of having something look just like something else. And because it looks just like something else, it satisfies same properties. We call that isomorphism. We have many analogs of that just like the subgroups. For example, the isomorphism is just like bijection in, bisimulation in logic, or homeomorphism in geometry, or let's see, isomorphism, a morphism of linear orderings. You can tell I study logic, so that's why I have a lot of logic examples. Anyways, so first thing we talk about is permutation group. So okay, we have, for example, three objects. Oh, by the way, this is the homework. Chapter 5, subgroups and generators, you 5.5, 5.7, 5.10. For chapter 6, which is the permutation group, do 6.1, 6.3, 6.11. And chapter 7, which is the isomorphism group. Don't worry, we'll be covering homomorphism very soon. I think isomorphism has better intuition. Also Armstrong chapter 7, so, and homomorphism all the way chapter, 12? Far away. So we'll follow Armstrong. Good to be consistent with the book. So chapter 7, isomorphism, 7.1, 7.3, 7.5. I think these are good. So let us start. So we have three objects. Okay, I can take the objects and I can do nothing. Doing nothing and having the first object still in the first position, second object is on the second position, and third object still in the third position is called, you call this the identity. But then I can permute these objects, right? I can take, for example, the third, put it the second, the first, I leave it the first, and I can, for example, leave it like this. Notice that we say the first element goes to the first. So we put nothing. But the second element goes to the third, and the third goes to the second. Call this a two cycle. So essentially, so for example, also, one goes to 3, right? We put the first one down. Have it go to 3. 3 goes to the second position. And second position goes to first position. This is a 3 cycle. So what essentially is happening is we look first where the first element is moved to. And then we say first element, if it goes to itself, we get rid of this element. Because we remove one cycle. One cycle, not important. Then we look at the next one that has not occurred. For example, 2. Or actually first, if this is another element, let's say 3. So 1 goes to 3. Then we look at 3. We look at where 3 has went. 3 has went back to 1. Because it goes back to 1, we go close cycle. And 2 is still at 2. So this is still, so we don't put 2. We don't include 1 cycles. permutation has always been difficult to explain without talking about bijections. And I think I have not yet, I taught you that. Remember, it has to do with animals and cages, and every cage has to be filled, and no two animals per cage. I teach another time. But I think it'll be easier if I just talked about permuting rather than bijections. So, rigorously, we write down the first element. So whenever the 1. So we start out at 1. Start at 1. And see where it goes. That's the first thing you do. You start at 1, you see where it goes. Whenever, and then, okay. If it goes back to itself, so in other words, for example, 2 stays at 2, you don't include it in the cycle. We make a new cycle, starting at the next element, not yet mentioned. So for example, if we have 1, but the thing is 1 goes back to itself, so we don't include it. So what has not been mentioned after 1? 2. So another example, if we have 1 loop back to, so okay, 3. Follow it. Follow the chain until it goes back, until it loops. Okay. So in this case, we have 1 go to 3, 3 goes to 1. So we close it. Then we look for the next. Look for the next that is not mentioned. So here, 1 is mentioned, 3 is mentioned, but 2 is not mentioned. So we start over with 2. So we have 1, 3, but 2 loops back to itself. So we do not include it. So we can do this instead of with 3 objects. We can do this with 4 objects, 5 objects, 2,257 objects, and call this the group of permutations. And we form it, well, first of all, these are the permutations. For 3 objects, there's exactly 3 factorial permutations, which are E, 1, 2, 1, 2, 3. 1 goes to 2, 2 goes to 3, 2, 2 and 3 switch. 1 and 3 go switch. I think it's like, yeah, 1 goes to 3, goes to 2. I think this is it. Yeah. These are the 6 permutations. Okay. So notice that we can form this group under composition. So for example, let's see. So here's the thing. First of all, you want to form a group, right? First, I claim this group, it can be formed under composition. Simple. I permute it first from 1, 2, 3. Take alpha. And then I perform a permutation alpha. Let's say like this. But also, I can then perform another permutation, beta. And then, so we say this is the final permutation. This is still a permutation. So, okay, let's do it rigorously now. Let's do an actual example. And by the way, composition on the left, the one that on the right are the ones that occur first, and then beta is one that occurs, you apply after you do it. So, okay, let me give you an example. Let's say alpha equals the cycle. Oh, Okay, pause.